Stokes theorem, this tells you that on MF, basically on this surface we are integrating over, the omega, basically the symplectic form, or this guy, I call it alpha, which is equal to d alpha, when you restrict it on MF, it's actually 0. Or turn that into plain language, we need this. Equal to 0 for all k and l. Okay? You can write it out in a component. So to show this guy is true, there are various ways. So in the notes, I provide the way in the differential form. But we can write it out just simply in terms of coordinates. It might be quicker. Well, actually, it may not be quicker, but it might be more apparent to people. So, so we know that MF, Fi equal to a constant. Then that's basically saying, if you're taking the derivative, so now the momentum F still depends on implicitly on the momentum PL, but PL itself is a function of coordinate. But whatever you are doing, the other side is constant, therefore the derivative is 0. So if you multiply this by a summation of df by dpk, then sum over all k's, and exchange the index of ij and ji, and subtract them. So I should write it like this. Then basically we obtain the following. The Fi, Fj, Poisson bracket, that simply comes on first term, plus KL, so there's some rearranging. Equals to 0. Instead of 0, subtracting 0. So that's basically where the commuting property of conserved charges comes in. Okay? So because we know if this is true, this is 0, and the df by dp L generally are not 0. So that implies that this can only happen if this guy is 0 for k L equal to n. And this condition is sufficient to ensure, let's say when you do the loop integral, okay, along this loop to precisely vanish on the surface NF. So, and this is the Liouville. This is the power of the Liouville theorem. Okay, so I think this is a good place to stop. So I think in the next lecture, I will tell you. So now, hopefully you, even though you may not be able to follow all the steps here, but hopefully I managed to hammer you the idea that the conserved charges and the fact they are commuting plays a very important role in basically to solve a classical dynamical system. And once you have those guys, then basically your problem becomes actually rather straightforward. And in the next lecture, I would like to talk about whether one can actually systematically to construct those conserved charges. Okay, so all right, so let's take a break here until 11.